As the city grinds to a halt, the promise of a different future takes flight above the endless congestion. Within seconds, it disappears into the sky. No highways, no red lights, no traffic. For more than 100 years, humans dreamed about flying cars. Most people thought they belonged in science fiction. If we adjust the wing angle by 3 degrees, we increase efficiency. Let's run the simulation again to confirm the aerodynamics. And some experts believe the first large-scale flying car networks could completely change transportation forever. But here's the real question: how do flying cars actually work?
If we adjust the thrust vectoring here, we reduce drag by 15%. But what about the battery degradation at that output?
These machines are not just cars with wings. They are closer to miniature helicopters combined with high-performance electric aircraft. The AI is showing a green light for the propulsion test. Good, let's initiate the chamber sequence. How do you safely move people through crowded skies every minute in major cities? And this is where things get surprising. The global race for the skies is heating up. Billions are at stake, and these prototypes are pushing the limits of aerodynamics.
The idea of flying cars is older than modern computers. In the 1940s and 1950s, inventors across America...
Magazines showed futuristic cities filled with tiny flying vehicles moving between skyscrapers. Some companies even built prototypes.
But almost all of them failed. Why? Because early flying cars were extremely dangerous. They were heavy, hard to control.
But decades later, everything changed. Electric motors became smaller and more powerful, and suddenly engineers realized something important. Instead of building cars that could also fly, they could build lightweight electric aircraft designed specifically for short urban travel. Today, many companies call these vehicles eVTOLs, electric vertical takeoff and landing aircraft. And unlike traditional airplanes, the turbulence decreases significantly if we adjust the wing sweep.
Agreed. Let's run the simulation on the new parameters.
Gravity compensation is stable. We have achieved full weight distribution across all vectors.
The tensile strength is exceeding projected limits at this junction. And the RLA readings confirm structural integrity across the lattice.
Carbon fiber is incredibly strong, yet much lighter than steel. Some flying car frames weigh less than half the weight of traditional automotive bodies. Look at the turbulence pattern here.
It's consistent with the CFD model. Rerunning the optimization sequence now.
Even tiny design changes can affect stability. A slightly different wing angle, a small rotor adjustment, or a sharper bite. But here's the interesting part. Many modern flying cars don't actually use traditional airplane wings during takeoff. Some designs use 4 rotors. Others use 8. Some even use 16 or more small electric propellers working together. This creates redundancy, meaning if one motor fails, the aircraft can still remain stable. And stability is everything. Check the alignment sequence on Platform 7. Rerouting the auxiliary servos now. Looks stable. Workers place the carbon fiber layers into giant molds. Then liquid resin is added. The components are compressed under intense pressure and finally baked inside industrial ovens called autoclaves. Inside these machines, temperatures can exceed 250 degrees Fahrenheit. Pressure forces the layers together into an ultra-strong composite structure. After curing, robotic cutting machines trim the parts with millimeter precision.
Confirming cabin alignment. Bay 4.
Structure secure. Proceeding with rotor installation.
The resonance frequency is stable. Joint integrity confirmed.
It's well within tolerance. The reinforcement holds.
Unlike normal cars, flying cars must survive both road-level impacts and airborne aerodynamic forces.
And this is where things become incredibly expensive. A single aerospace-grade carbon fiber component can cost hundreds or even thousands of dollars, far more than traditional.
Next comes the heart of the flying car, the propulsion system. The propellers are carefully engineered for maximum efficiency. Even small imperfections can create dangerous vibrations.
These systems constantly adjust power output hundreds of times every second, so onboard computers continuously stabilize the vehicle automatically.
Now comes one of the biggest challenges in the entire industry: batteries. Flying requires enormous amounts of energy, much more than driving.
A vehicle must continuously fight gravity, which means battery efficiency becomes critical.
Cooling systems are added to prevent overheating. If batteries overheat during flight, the consequences could be catastrophic. Battery weight remains one of the biggest limitations preventing long-distance flying cars. Many can currently travel only 20 to 150 miles per charge. Large touchscreens display altitude, speed, battery levels, air traffic data, weather conditions, and navigation systems. Thousands of vehicles moving through invisible aerial highways above cities. Before a single passenger can fly, the aircraft must survive brutal testing. This phase can take years. Rotor blades spin continuously for thousands of hours. Motors operate under extreme heat. Battery packs are punctured, crushed, and overheated intentionally. Look at the wake turbulence here.
Zooming in now. It looks stable, but the pressure differential is significant.
Hydraulic machines bend and twist the airframe repeatedly. Some components endure forces far beyond normal operation.
Critical malfunction detected. AI stabilization engaged. Prepare for emergency landing.
Check the power fluctuations on assembly line 4. The stabilizers are running hot.
I see it. Rerouting auxiliary coolant now. Factories must combine automotive manufacturing speed with aerospace-level precision. That combination is extremely hard. The AI detected a subsurface anomaly at coordinate gamma 12. Run a tertiary scan on that vector immediately.
Cities may eventually build entire aerial transportation networks. This is where the industry becomes bigger than just vehicles.
Imagine traveling across a crowded city in 10 minutes instead of 90. That's the promise companies are selling: urban air mobility.
Some experts believe flying taxis could reduce pressure on roads, especially in cities with severe congestion.
We're losing altitude too quickly. Stabilize the craft.
Look, they made it. The delivery is safe.
Look up there! The traffic control is down.
We have to find shelter now, before the storm hits.
We have an anomaly in the southern quadrant. See the spike?
Yes, adjusting the parameters now. The system is handling it.
Flying cars are currently some of the most expensive transportation machines ever designed. Many companies spend billions before producing a single commercial aircraft.
The structural integrity failed at Mach 2. We need to reinforce the fuselage before the next run.
Carbon fiber airframes, electric propulsion systems, battery packs, AI computers, cockpit electronics, every component is extremely expensive. The laser scan on the starboard panel is complete. Data looks nominal, Dr. Eris. We are clear for the vibration test. But mass production could eventually reduce costs significantly. Future flying cars might one day become affordable for upper middle-class consumers. This business model works similarly to ride-sharing services. Passengers book short flights through mobile apps. A single air taxi could complete dozens of trips daily. A 20-minute flight costing $120 could generate thousands in daily revenue. Now subtract charging costs, maintenance, insurance, software systems, and landing fees. But autonomous flying taxis could reduce costs dramatically. This is why investors are pouring billions into the industry. Because if urban air mobility succeeds, the market could become enormous. For For more than a century, flying cars existed only in imagination, a futuristic dream seen in movies, comics, and science fiction.
The stabilization during the transition phase looks solid.
Yes, well within tolerance levels, ready for the next flight test. Governments are testing aerial transportation systems, and billion-dollar companies are racing to shape the future of mobility. Will flying cars completely replace roads? Probably not. But they may transform transportation in ways the world has never seen before.
We actually did it.
Look at it go.
Subscribe to Future Factory and turn on the bell icon, because the future is already being built.